Great. Okay. Well, hi everyone. My name is Benjamin Bichsel, and I'm presenting dpFinder, another system for finding differential privacy violations by sampling and optimization. This is joint work with Timon, Dana, Petter, and Martin, and we are all from the SRI lab at ETH Zurich. So let me just quickly recap the basic setting of differential privacy, where we have some kind of database that contains sensitive information about users, and we run some kind of algorithm on this database. In this example, we report the number of users or the number of people in the database that have a particular disease. Then we get this number and we publish it, which in particular also means that an adversary is allowed or is able to see this data. So typically, we will not release this data just like that. Instead, we will randomize the algorithm. In this particular example, I added a bit of noise to the end. So instead of reporting the true number, like 7, we will report a slightly obfuscated number, like 7.5. Now, a valid concern of individual users in this database is, well, what about my privacy? Obviously, this 7.3 value leaks some information about whether or not I have a disease. And the answer that differential privacy gives is in terms of a hypothetical database. Differential privacy says that, well, if we change the data of this individual that's concerned about her data, then we get a different database, and we can of course look at the output of the randomized algorithm for both databases, and we can check if an attacker is even able to determine if the original database was used or the hypothetical one. If the attacker is not able to do this, then it's safe to use the original database because it doesn't really matter if you change the data or not. Now, looking at this a bit more abstractly, in differential privacy, we have like an original database X, a hypothetical database X prime that is a neighboring database to X. Like you can formalize this some more depending on your taste if you want. And then you run a randomized algorithm F. You get some kind of result, f of x or f of x prime. And the task of the attacker is determining if she's seeing f of x or f of x prime. The most general way to address this task is just by checking if the output that you're seeing is in some set. Now, differential privacy is trying to prevent the attacker from determining if she's seeing f of x or f of x prime. And the way the way differential privacy does this is by asserting that the probability that the attacker's check succeeds for f of x and for f of x prime is roughly the same. So I formalized this here, right? This is a standard notion of epsilon differential privacy, which says that the ratio of the two probabilities is at most e to the epsilon, which is roughly 1 plus epsilon. Now, differential privacy induces a number of challenges. First of all, it's very hard to prove epsilon differential privacy. And even if you don't care about the formal proof and just informally want to investigate if your algorithm might satisfy epsilon differential privacy, this is quite hard, which is also witnessed by a number of buggy algorithms that have been proposed in the past. Another issue that you would probably expect is that there is no complete proof strategy out there. So whatever proof strategy you're trying to do, you're not guaranteed that it always works. And finally, even if you even if your proof strategy works and you get a proof for epsilon differential privacy, you will only get an upper bound on the true epsilon, meaning that it's possible that at some later point someone else does a better analysis and will get better results even for the same algorithm that is under investigation. So we address these challenges by in this work with dpFinder by looking for counterexamples to epsilon differential privacy, which is a triple of original database, hypothetical database, and attacker's check that violate epsilon differential privacy. So that just means that the two probabilities are substantially different, meaning that the ratio is more than e to the epsilon. We can do some standard algebraic operations on this and realize that, well, actually what we're trying to do is finding x, x prime, and phi such that the log ratio of the two probabilities is large. And in this work, we're trying to maximize this log ratio, which we call in the remainder of this talk epsilon depending on x prime and phi. The way you should think about this work is in terms of bounds on the true epsilon. Let's say we have some kind of algorithm where we have a proof that this algorithm satisfies 10% differential privacy. We would hope that our tool then finds a counterexample to say 5% differential privacy, and this means that the true epsilon that is satisfied by the algorithm is somewhere between 5% and 10%. Of course, it would be even nicer if we could find a counterexample to 9.9% differential privacy, which would then mean that essentially the true epsilon is roughly 10%. What's even more interesting is if we find a counterexample to 15% differential privacy, which just means that the original proof was wrong. And seeing existing literature on this scenario is not entirely unreasonable to expect this. And in our evaluation, which I will quickly show to you later on, we show that we get precise and large epsilons that are even close to the known upper bounds for the algorithms we investigated. So, as I said, what we would like to do in this work is we like to maximize the epsilon that depends on x prime and phi. And to do this, we need to address two key challenges. First of all, it's very expensive to compute the epsilon, even if you know x prime and phi. What we do to address this challenge is we replace the epsilon by an estimate. It will not be exactly the original epsilon, but it will be close enough. And we also want to figure out how close it actually is. I will talk a bit about that also. Now, the second challenge is even after we have this estimate, it is still hard to find good triples. This means that the search space is sparse, meaning that only few triples actually lead to a large violation. And the way we address this challenge is by replacing the estimate by a differentiable version of it, which allows us to then use off-the-shelf numerical optimization to gradually improve the counterexamples we're seeing. Now, let me first go the first step, which is estimating the epsilon by sampling. And the way we do this is remember, the epsilon is just a log ratio of two probabilities, and we can estimate this by just estimating the two probabilities separately. And the way we can do this is we can run f of x many times and check if the attacker's check succeeds for these examples, and the relative frequency of this will then tell us what our estimate of the probability is. Let me visualize this quickly a bit. So we start off with some database x. We run f of x many times. We get a lot of outputs, and we check if the attacker's check succeeds for these outputs. In this example, the attacker's check succeeds 2 out of 3 times, which means that our estimate will be 2/3. Now, a crucial question when we are doing this kind of estimation is how precise is our estimate? Here I'm showing you a concrete example where we think we have found a counterexample to 9.9% differential privacy, but actually our estimate for this counterexample is very imprecise. It's like plus minus 10%, which essentially means that our estimate is not very useful. What we would like to have is, of course, a much higher precision. And in this work, we aspire to a precision of 2 times 10 to the minus 3. Which is a lot higher than 10%. And this allows us to give a reasonable estimate of what exactly the epsilon of our counterexample is. Now, the precision of epsilon, of course, depends on the precision of our estimates for the two probabilities. And the precision of these two estimates depends on the sampling effort. So I will quickly walk through how we can determine the precision of epsilon based on a given sampling effort. And in our tool, in dpFinder, we don't actually do it this way. Instead, we start from a desired target precision epsilon, and we infer the sampling effort that's required to reach this target precision by exponential search, meaning that we gradually improve or exponentially improve the sampling effort until we reach the desired target precision. Now, On this graph, you can see that unfortunately, reaching a high precision is very expensive. So here, again, we're targeting this precision of 2 × 10⁻³ and the blue curve shows you the sampling effort you need if you want to estimate the epsilon up to this precision with a confidence of 90%. What you can see here in particular is that even if we are estimating moderately large probabilities like 10%, we will need more than 10⁸ samples. So this is very expensive, in particular if we want to do this during the search, which will consist of a lot of steps. And the nice thing about Hoeffding's inequality here, so the blue line is is using Hoeffding's inequality, is that we get probabilistic guarantees, which is nice if we want to report a final counterexample to the user. We could do this in this case, but during the search, this is very expensive. So we'd like to do better. And one thing we could do is use a heuristic that observes that, well, essentially, our estimate is distributed according to a Gaussian distribution, according to the central limit theorem. This is only true asymptotically, but in practice, this is a reasonable assumption to make also for moderately large sample sizes. This will reduce the required sampling effort a bit, but still, it's very expensive. So we still need 10⁸ samples to estimate probabilities of 10%. And we will not be able to do much better than this unless we change the sampling method. And this is what we did in this green line. We changed the sampling method to induce correlation between the two samples, which I will quickly walk through in a bit more detail now. And what you can see here is that depending on how much correlation we induce, this can lead to improvements of something like 4 orders of magnitude. So I will not go through all the details of how this works. The exact details are in the paper, but just to name drop a few techniques and to give you a general indication of how you could approach this. Remember or recall how we did the estimate of this probability that the attacker's check succeeds for the database X. And we produced a lot of samples and we checked if the attacker's check succeeds for those. What we can do now when we do the same process for checking how often the attacker's check succeeds on the hypothetical database X prime is we can use the same randomness. Remember, the algorithm F is randomized, and we can just use the same randomness here, which will mean that typically, this is what we empirically observe, that the outputs are highly correlated. As a consequence, this means that our estimates follow a joint Gaussian distribution that is highly correlated. And if we can determine this joint Gaussian distribution, which I visualize here, this gives us a joint Gaussian distribution of the two probabilities, then using existing work, we can estimate the distribution of the likelihood of epsilon, which in turn allows us to estimate the confidence interval for epsilon. As I said, the details of this are in the paper, but this was just like to give you a quick overview of the relevant techniques to do this. So what you should take away from this part of the talk is that precision is important, and depending on what kind of precision, depending on the technique we use, we can reach the same precision using orders of magnitude differences in the sampling effort. So let me also talk about the second step, which is actually finding good counterexamples. Before we just estimated the epsilon for a particular counterexample. Now we want to iteratively improve those. And the way we do this is by making the estimate differentiable. So recall that we wanted to maximize this estimate, but the problem is that this estimate is a log ratio of 2 estimates, and these estimates are not actually differentiable. So you can see here that the check function that I show here is not differentiable. This is because already the original algorithm is typically not differentiable because it does like control flow, if then else, stuff like this. And also the attacker's check itself does usually some kind of comparison. So this is in general not differentiable. But what we can do is we can view this attacker's check as a program, and we can change this program using syntactic modifications. I show you a few of these syntactic modifications here, but the details are actually not that important. They are in the paper. But what is important to note here is the general goal of this transformation, which is, well, first of all, we would like to make the check differentiable. And second of all, we would like the differentiable version of this program to give us some indication of what direction we should go towards to get better counterexamples. And so I wrote down here that this transformation should preserve semantics. This is, of course, not true in general. If the original check function was not differentiable, then we cannot make it differentiable and preserve semantics. But empirically, we can slightly change it to still stay reasonably close to the original version, but get an indication of where our search should look for next. So once we have made this estimate differentiable, we can use off-the-shelf optimization techniques to solve the optimization problem. In our case, we use SLSQP. We start from a random starting point, and of course, if we don't like the result that we get from that random starting point, we can always restart. There are a few technical questions that can come up that I wrote down here. The answers to these are in the paper. Now, let me also quickly take the time to point out the main differences to this concurrent work that you just heard about before, which was done by Ding et al. And already the high-level problem statement is slightly different. Ding et al. Compares to a threshold, epsilon 0, and try to figure out if the algorithm satisfies or does not satisfy this level of differential privacy, whereas we try to maximize, so we're trying to find the globally best epsilon. This is not always possible, but this is like the inspiration of this work. And as a consequence, the approach is also different, of course, because Ding et al. Use statistical tests to check if this inequality holds. So if the epsilon is above the tested epsilon 0. And we, in contrast, we estimate the epsilon, and we also provide confidence bounds to give an indication of how good our estimate is. And the most significant difference, in my opinion, is the way the search works. Ding et al. Use patterns that empirically lead to large violations, whereas we use gradient descent, which essentially boils down to incrementally improving the counterexample we are seeing right now. Now, I have shortened the evaluation a bit, and I only answered 2 important questions. More questions are answered in the paper, so the questions I answer here is how precise is the differentiable estimate, and how efficient is dpFinder in finding violations compared to random search. And for the first question, we use an exact solver, psi, to determine the ground truth. Again, just like for Höfting's inequality, this is feasible for the counterexample that we are seeing in the very end, but it would be too expensive to do this during the search at every iteration. So here I show you a box plot that tells you like what kind of epsilons we were seeing for the algorithms that we looked at. On the x-axis, you see the different algorithms that we tested on. They were taken from the literature and have been investigated before, in particular also for upper bounds. On the y-axis, you see the epsilon, whereas for every algorithm, on the left-hand side, you see our differentiable estimate, and on the right-hand side, you see the ground truth as computed by the exact solver. Overall, you can see that our differentiable estimate is very close to the true epsilon. Now, this is not the true epsilon that I mentioned before, but it's the epsilon we're seeing for the given triple. And what you can see is that sometimes, like for example here, there's a slight deviation. And the reason for this is that we replaced our estimate by a differentiable version of it. And therefore, this doesn't exactly preserve semantics. But overall, the differentiable estimate is very close to the true epsilon. And the next question was how efficient dpFinder is in actually finding high violations as compared to random search. The basic setup of this box plot is essentially the same, but now on the left-hand side, we describe the epsilon that we get for a random starting point. And on the right-hand side, we show the end result we get after optimizing starting from this random point. And what you can see here is that overall, using gradient descent to improve the counterexample significantly helps and increases the quality of the epsilon. And in particular for some algorithms, we see kind of the ideal result, which is that for random starting points, the results are highly inconsistent, whereas if we use optimization, we get significantly better results that are consistently always also at the known upper bounds. I didn't show this before, but the blue lines that you can see here are the known upper bounds. And you can see also in particular that for many algorithms, we get really close to these upper bounds. With this, I would like to conclude my talk. Thank you for your attention.
Excuse me, my question is just the very last slides you presented on the accuracy of the estimation.
Yes.
And how practical is your solution is in finding those let's say, violations. But there is something else, which is the efficiency of the algorithm. As you mentioned, you may require a lot of samples to find those estimations, right? My question is, did you dig into the, let's say, all existing solutions in control theory, like a Monte Carlo solution or particle filters, to just reduce that number of samples to something which is good enough for your problem? Is it the best solution that, in terms of efficiency? And do you have any curves showing the efficiency? How many samples do you require for getting to that accuracy level?
So you're asking only about the estimate, right? Not about optimization. Yes. Because like for the optimization, you could also use different techniques, but you're asking about the precision of the estimate. Right. So in the paper itself, we also show like how many samples we require for, we show essentially like a similar box plot as you can see here that tells you like how often we needed which number of samples. And there you can see that depending on the starting point, this significantly varies. So depending on where you start, the number of samples you need significantly varies. And empirically, we also checked that, I guess this is what your question boils down to. You would like to know if, instead of using this multivariate Gaussian kind of thing with the correlation, if you could get better bounds on this, right? And we do not report this in the paper, but we investigated this manually a bit, and it seemed like with this approach we actually get like pretty tight bounds. So we checked manually that we like the precision of our estimate is roughly what we would expect according to our
my question is not about the precision; it's about the number of samples required. You may get with some estimation solution to a certain precision with, let's say, 1,000 samples, or with less or more samples. Like that number of samples that you require to get to the certain precision.
I'm not sure I understand your question. Maybe you should take it offline.
Yeah, sure. Thank you.
So I was wondering if there are any toy problems where applying your framework leads to a convex optimization problem.
That's a very interesting question. I mean, like a related question, I guess, is if there are also optimization problems where it's immediately differentiable, right? That would be an even more basic question. And I don't know, like typically, especially because the attacker's check is usually trying to check like, oh, is it more than this? You immediately have some kind of non-differentiability. So we haven't investigated this in detail. I'm guessing that even if you can find this kind of counterexample, it will not be this kind of algorithm where this works well. It would not be particularly interesting, right? Because we care about interesting algorithms. But what I can tell you is just that especially machine learning has been applying this kind of gradient descent optimizations successfully to all kinds of problems, also non-convex ones. So it's reasonable to expect that this works well also in this setting.
I again have the same question as before. neighboring relations. What if you use neighboring relations that are more complicated? I know also have an example. What if you have ICU data? You have medical data and traces from people that come to an ICU, and there you have a different neighboring relation, right? So you might be interested in people that are or that only differ in age a little bit. That's your sensitivity function. What kind of neighboring relations can you, or sensitivity functions, can you support? How far can you go?
Right. So this essentially boils down to what kind of optimization mechanism we use. So we use this SLSQP, which is an off-the-shelf optimizer, and this supports hard constraints for the neighborhood. And in particular, like the kind of constraints that we looked at is, this is at most one away, which works well for this kind of neighborhood relation. If the neighborhood relation is more complicated, then I'm guessing at some point SLSQP cannot express this, and then you're done, right? So what you can do instead in this case is maybe fall back to this other work where you have patterns. I'm guessing for patterns this would work a lot better, right? Because then you can just check for all the patterns if the neighborhood relation is satisfied, and then you check for those. And you would still get benefits from parts of our work, in particular like the reduced sample size by correlation. You could still use that.
And I guess, yeah, if you have a differentiable sensitivity function, you might be fine with this.
Yes.
Thanks.
Okay, so thanks again, and thanks to all the speakers.